Alrighty, good morning. Let me switch here. Webcam. How's it going? Um, if you have any questions, homework questions, you can go ahead and drop them in the chat right now. Just let say the chapter and the problem number. And if you're using something other than the 6th edition, make sure you note that you're using something other than the 6th edition. Um, let's see. All right. Right. So, first, some quick announcements. I made a new page in the home module for the annotated lecture slides. So you can go there to find those, right? Those are the ones that I've drawn on in class. So if you want to look at those, download those are there. And I will sort of update after every class period when I get those loaded, I'll link those there. So you kind of have one place to go and find all of them. I'm sorry I haven't done the chapters yet. I don't know if you guys have gone and looked at the YouTube for chapter 3 yet. I haven't gone through and added, the segments and timestamps, but I'm planning on doing that after class today. The biggest announcement, right, is that we have a test tomorrow. I changed that format so you can take that test anywhere from 7 a.m. to midnight. I think I said before you could start at midnight. Like if you started at 11:59, you'd still get the full 45 minutes. I don't think that's the case. I'm hoping that none of you are planning on doing that anyway, but I will send out an announcement to make that clear. There will be calculations to do, right? A lot of the stuff that we've done up till this point has been dimensional analysis, unit analysis. Dimensional analysis, unit analysis, that kind of thing. So you're going to be doing calculations. There's no way around it. But it'll be 30 questions, and you'll have 45 minutes to do that. This test is shorter, and then every test is going to get longer as we go, right? Because we're going to add more questions from the newer chapters, and I'll take some of the questions out from the previous chapters. And expect to see questions similar to what we've been doing in lecture, right? So it's probably your best source for looking at those. Or best source for studying those and the homework problems. There's not a whole lot of concepts yet, so there will be things though like asking. Today we're going to talk about atoms. So I'll ask, what is the name of the element that has atomic number 43? But we'll cover that today. So there'll be a lot of those kind of questions. At this point, I think it's all multiple choice. There might be some different kind of stuff. So there might be some, properties, chemical properties and physical properties. There'll be 2 boxes, and then there'll be a list of properties, and you drag those and sort them into the boxes that are appropriate. All right. And I also wanted to mention, if you have questions, like if at night you want, obviously you can always text me and I'll try to respond as fast as possible. But if you want to see questions gone over in class like this, you can always send me questions like that, and then we can go over those in class and have them recorded. So I did get a couple questions that way, and let me actually open up. Let me open up this. The question was about problems 74 and 73 and 74, which is actually from today's homework. I'm sorry, I've misled you. I'm actually going to go over these later because this is for Chapter 4 homework. And so I will try to remember to cover these as a part of that when we get to it into the chapter. Okay, so let's bring up the iPad and get started in here. If there are no questions about anything else. Sweet. Okay. So, atoms and elements. So, up till this point, right, we sort of mentioned atoms. we've mentioned we mentioned that atoms are elements, I think, and we've talked about putting them into categories. We talked about how the properties of individual atoms work together to create the properties that we see, right, at our human scale. So like, why is plastic the way it is? Well, it's because of the atoms. And so you can make predictions based on which atoms are incorporated, which molecules are incorporated. So today we're going to learn more about the atom itself. Right, and we've talked about this already. All matter is composed of atoms. Atoms are the building blocks of everything you hear, feel, see, and experience. The properties of atoms determine matter's properties. The atom is the smallest identifiable unit of an element. So if you broke, if you took, for example, my Apple Pencil and broke it down as far as you could, just kept dividing it in two, cut it in half, cut that in half, cut that in half. If you just kept going, eventually you would hit a point where you could cut nothing in half, and that would be an atom. There are about 91 different kinds of atoms that occur naturally. There are there are lots of elements on the periodic table at the bottom half, or not even the bottom half, like at the bottom of the periodic table, that have been man-made in, what are they called? Well, like the Large Hadron Collider, so particle colliders, or doing nuclear chemistry. But there are 91 that occur naturally. Atoms are incredibly small, and this is kind of a way, I gave you that example. If you took an atom, the atoms in like a grape or a blueberry or something, you took all those atoms and you made them the size of that blueberry or a marble, they'd cover the world to a depth of 6 feet. If every atom within a small pebble was just the size of the pebble itself, the pebble would be larger than Mount Everest, or the pile of atoms created would be larger than Mount Everest. Let that sink in. Like, really try and visualize what that would look like. This tiny pebble blowing up to the size of Mount Everest, or here in the valley, larger than the Sierra Nevadas. So it was, I looked up how to pronounce this. Leucippus, I think is how you pronounce it, and Democritus were the first sort of recorded ideas of the atom. And it was Democritus that suggested, like I was saying with this Apple Pencil, if you broke this into smaller and smaller pieces, eventually you would end up with a tiny indestructible particle. And Democritus called those particles atomos, or atoms, meaning indivisible. And from there, it was a long time. So that was back in, somewhere between 460 and 370 BC. It wasn't until over 2,000 years later, that this was widely accepted in John Dalton's atomic theory. And we mentioned this a little bit, but his formal theory is that each element is composed of tiny, indestructible particles called atoms. That all the atoms of a given element have the same mass and other properties that distinguish them from the atoms of other elements. And then atoms also combine in simple whole number ratios to form compounds, right? Like we talked about with water. If you have a water molecule, there's some things that you can't say enough. You have a water molecule, right? We have our oxygen, I'll use a different color, and our two hydrogens. Every water molecule is like this, with one oxygen and two hydrogens. So evidence for the atomic theory. So scientists at IBM used to be a much more common name. They're now mostly in the business space. But they used a special microscope called a scanning tunneling microscope. And we saw this before. They did it in Japan as well, where they drew the kanji for atom. But here IBM, in somewhat a self-centered way, wrote out IBM. Now, the atoms are actually not cone-shaped like that, but they are spheres in general. The cone shape is just a peculiarity of the instrumentation, as it says here. So J.J. Thomson then later on discovered a smaller particle called the electron. And electrons are negatively charged. They're much smaller and lighter than atoms, and they're uniformly present in many different kinds of substances. Thomson's theory of how atoms and electrons work together is sometimes called the plum pudding model. And if you look up plum pudding, you'll find that it's not pudding at all. I was fairly disappointed. But the idea is that you have this positively charged sort of sphere of charge, and then you have electrons that are dispersed within it. I don't know if you've ever had like a fruit jello, and there's like chunks of fruit suspended in the jello. That's kind of the same idea as the plum pudding model. Then in 1909, which if you think about it, 1909, I mean, it's a long time ago, but it's not that long ago. Ernest Rutherford, though, conducted an experiment where he set up a beam of positively charged alpha particles and shot them at a thin sheet of gold foil. Now, if our model of the atom is that it's this sort of nebulous, positively charged sphere, and it's got these electrons interspersed throughout it, you'd expect that most of the particles, in fact, you would expect that all of the particles would pass directly through it with very, very little deflection. However, when Rutherford conducted this experiment, he found that some of these particles, and I'm going to zoom in here, some of these particles almost came back directly at him and were highly deflected away from the original paths. And that's what you can see here. So he concluded that there's something else going on here. And so if the plum pudding model is correct, right, we would see them go all straight through. But the actual result was that they bounced back. Some of them, a very small number, but some of them did. And so his direct quote is, "The plum pudding model is about as credible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you." I mean, it'd be like, to sort of put it into modern terms, if you took your rifle out to the range, if you have a rifle, I don't know, and you fired it at Jell-O, and those bullets bounced back. So he concluded that, let me move my head here. So he concluded that instead, there's a small, very dense nucleus at the center, and rather a cloud of electrons that surrounded that. And this is what we know today as the nuclear theory of the atom. So most of the atom's mass and all of its positive charge are contained in this small core called the nucleus. And most of the volume of the atom is actually empty space through which tiny negatively charged electrons are dispersed. So if you were to actually zoom in, you would see that everything is actually mostly empty space. The number of negatively charged electrons outside the nucleus is equal to the number of positively charged particles, which we'll learn are called protons, inside the nucleus, so that the atom is electrically neutral. That can change. They're not always electrically neutral, but for an electrically neutral one, the charges are equal. So later work showed that the atom's nucleus contains both positively charged protons and a neutral particle called neutrons. And the dense nucleus really makes up more than 99.9% of the mass of the atoms, but only occupies a small volume. And then the electrons are then distributed again throughout the outside, kind of like water droplets in a cloud. So you've got teeny tiny nucleus in the center, and then a cloud around it. Oh, I thought that was going to be okay. Well, so protons and neutrons, very similar masses. And then electrons have almost negligible mass. So the atomic mass unit is what we use to talk about masses of protons and neutrons. And it puts things in an easier scale to understand, because if you were to talk about the mass of a proton in terms of grams even, it would be something on the order of like 10 to the minus, I'm just going to take a guess. I actually don't know exactly what it is, but something like 10 to the minus 10, I'm sure. At the very least 10 to the minus 10, probably much more than that. But you could look that up. So the atomic mass unit, though, is defined as 1/12 the mass of a carbon atom with 6 protons and 6 neutrons. So if a carbon atom has 6 protons and 6 neutrons, we take that mass, divide it by 12, because 6 and 6, and that's 1 atomic mass unit. So you can see here that the electrons are... Oh, sorry. All I had to do was look at the slide, right? The mass in kilograms of a proton is 10 to the minus 27 kilograms. So 10 to the minus 24 grams. And then the mass of an electron, 10 to the minus 27 as well, but notice here that it's 1, 2, 3, 4, so it would be 9.1 times 10 to the minus 31. So it's 4 orders of magnitude smaller than a proton. 4 orders of magnitude being 1,000 times smaller in terms of mass. And then we can see here also that the mass of a proton is positive 1, a neutron is 0, and an electron is negative 1. So when we compare protons to electrons, again, oh, see, it was off here again. It's 2,000 times as massive. So if a proton had the mass of a baseball, an electron would have the mass of a grain of rice. The proton is nearly 2,000 times as massive as an electron. This was what I was thinking about earlier. If you look at something close enough, you would actually see that it's mostly empty space, because again, we have tiny nucleus and then a cloud of electrons. And where those atoms actually are connecting is at the intersection of these clouds of electrons. So all of this, let me use a highlighter, all of this space in here is essentially empty. There are electrons flying around in there, but pretty much everything is empty. So if you looked at it close enough, which you can't do with the naked eye, you can't do even with a microscope, you would need something like a scanning tunneling microscope, then you would see that most of it is empty space. So when we talk about electrical charge, it's in some ways similar to magnets, right? If you have the north pole of the magnet, it's going to attract the south pole of the magnet. Opposites attract. An electrical charge works just like that. It's a fundamental property of protons and electrons, and opposite charges attract each other, but like charges, just like magnets, repel each other. So if we combine a positive charge with a negative charge, they cancel each other, so that a proton and an electron, when paired, are charge neutral. So when we talk about atoms, you might then ask, well, what makes one atom different from another? And really the thing that determines the properties of an atom is the number of protons. And so the number of protons is what we use to identify them. And the number of protons in the nucleus of an atom is its atomic number. It's given by the symbol Z. So it's a helium. This is a Z. Oops, that's a highlighter. Right? The atomic number for helium would be 2. And the atomic number, Z, for aluminum would be 13. But we'll do more of that. The periodic table then lists all of the known elements according to their atomic numbers. And as I was mentioning before, you can tell which atoms are artificial, the ones that we've created. If you zoom in here and see that for something like bismuth, right, we have an exact atomic mass here. Not the atomic number, but the atomic mass, right? So this is the combination of protons and neutrons. But if you look at something like polonium or astatine or radon, I think radon is actually, but these other elements they're in parentheses here, so they don't have exact numbers. And that's because sometimes when you create these very, very heavy atoms with lots of protons and lots of neutrons, hold on. lawnmower outside. When you combine these together and create these very, very heavy atoms, they're not stable. They break apart. And we use elemental symbols to represent each atom as a shorthand, right? If we had to write out, like here, potassium, sodium, lead, mercury all the time, it gets very, very cumbersome, so we've come up with a shorthand. Most of the time, it's like the first letter or first two letters of the element, but that's not always the case. Most of them are based on the English name, but here are some examples. These aren't all of them. For example, if you know the atomic symbol for gold, whoops, the atomic symbol for gold is Au, which obviously, I can't remember exactly what the historical name is there. I believe it's Greek. But this is not exhaustive, this list. So it would be very beneficial, especially on tests. Actually, on tests, I'm going to give you a periodic table. So you'll have a periodic table. It's not going to have, I don't believe it has the names on it. It's going to have the atomic symbols. It'll have the atomic number, which I think for potassium is 1, 2, 4. It'll have the atomic number, and then it'll have the atomic mass as well. My favorite element is the element of surprise. Okay, so I figured out more how Zoom polls work. So if you can find your find a periodic table, there's one in the back of the book. Here's the Skillbuilder 4.1 poll, and go ahead and just take a little bit and try and write down or I guess answer the poll questions for which element is which. Okay, that's good to know. So it doesn't update for me until you've answered all the questions and hit submit. And the poll is anonymous. So, if you're afraid of getting it wrong, nobody's going to know. It's okay. Part of this is to get you to sort of practice the skills, as we're going along. Trying to keep you engaged. All 6 of you. Or I should say 5, because I'm one of the 6. Two votes are in. 3 votes are in. I was intentionally tricky on these. I wanted to throw you off. And it can be hard, right? The periodic table is a big table. There's over 91 elements because it includes the man-made ones. Okay, so I got all 5 votes. So yes, correct. The first one is sodium. And for the sake of this, made it. I mean, if you find sodium, if you find Na, you're going to find the atomic number. But so sodium is the first one, and its atomic number. And just so we're reinforcing, Z is the atomic number. Has 11 protons, right? Because the atomic number is the number of protons. Nickel is the second one. Right, and again, Z is 28 for nickel. And then for P, phosphorus. I spelled that wrong? I spelled that wrong. It's just a U. Z is 15. And the last one, got a couple of you, is tantalum. So I would definitely recommend practicing these so you at least have an idea of where they are. I guess if I hit end polling, then maybe you can see it. Oh yeah, I could share results. The results of the poll. Okay, I'll stop share results. Okay, so let's move on then. Now, one of the incredible things about the periodic table, when Dmitry Mendeleev proposed this, he proposed this idea of periodic law. When the elements are arranged in order of increasing relative mass, certain sets of properties recur periodically. So they're color-coded here on the bottom. So if you look at helium, and then neon, and then argon, what you find is all three of those have very similar properties. Same going for the other ones that match here, lithium, sodium, potassium. And, this is something that just kind of like arises out of nature. And so this really did spur on people to figure out, it's like, okay, whoa, that's weird. It's kind of weird when something like a pattern like this shows up in nature, because you're like, there's got to be a reason. And so you go on then to look for the theory. You say, well, we know what happens now, right? Periodic law is what happens. So we see this, right? If you increase the atoms or if you increase the number of protons, you end up with this periodic law. The theory then would be, why does that happen? And we'll get into that here in a little bit. So you can also look at a periodic table like this, the full periodic table, and you see that we have metals, nonmetals, and metalloids. And these are largely just grouped based on their general properties. And you can see the vast majority of the periodic table are metals. We'll talk about those on the next slide, but you can see here, if you go down this diagonal, that we have the metalloids, and then everything over here, and hydrogen, because hydrogen's a little bit weird because it's so small. But these are your nonmetals in green. So, right, so metals occupy the left side of the periodic table, and really, like the left 2/3, if not 3/4. And they all have similar properties. They're good conductors of heat and electricity. They can be pounded into flat sheets, which is called malleability. And they can be drawn into wires, which is called ductility. In fact, the malleability of gold, which gold is a metal, right? It's got it right here at 79. That is why Rutherford used it in his experiment, because he could pound it into a flat sheet, a very, very flat sheet. We can draw metals into wires, right? That's one of the reasons, one of the reasons I suppose that copper is used in most wires, or in good wires, they use copper. It's often shiny or lustrous. And metals tend to lose electrons when they undergo chemical changes. And we'll talk more about what that means. So some examples of metals would be iron, magnesium, chromium, sodium, gold. I mean, you can think of them off the top of your head too, right? Aluminum is a very common metal. Then nonmetals are the right side of the periodic table, right? Those elements that were in green. And they are generally solids. Well, they have varied properties, right? So almost all of the metals, aside from mercury, are solid. But the nonmetals can be solids, but others can be gases at room temperature. And they tend to be poor conductors of heat and electricity. They also tend to gain electrons when they undergo chemical changes. Some examples would be oxygen, nitrogen, chlorine, iodine. Carbon is another one. So like the graphite, if you're using a pencil, that's carbon. But oxygen, nitrogen, chlorine, those being common as well. The metalloids are a strange group that occur along that zigzag diagonal line. I think they were purple. The metalloids then, it's a transition zone. Woo, I won't say that because we have transition metals too. But the metalloids are sort of a hybrid between metals and nonmetals. They can also be called semimetals and have the mixed properties of the two. So semiconductors, silicon is a metalloid that we use all the time. It's in your computer, it's in every single electronic thing, because they can be conductive, but they can also be non-conductive. And so you can turn that conductivity on and off. Silicon, arsenic, and germanium are examples of some of those metalloids. Okay, Skillbuilder 4.2. Launch that poll for you guys there. So go ahead and classify each of these elements as a metal or non-metal or metalloid. So if you have your lecture notes, you can go back and, or yeah, the slides, right? You can go back and to that periodic table, take a look at that. Again, there's a periodic table at the back of your book. Make sure you're finding the right one. Cool, cool, cool. One response in. Two responses in. Guess I'll give you 20 more seconds here. And again, you know, don't worry about it if you get it wrong. Again, the polls are anonymous for that reason. But the more you participate, the more you're engaged, the more you learn. All right, I lied. I gave you 30 more seconds. We'll end the polling then. And then, okay, so we got sulfur is correct. That's a nonmetal. Whoops. Nonmetal. Chlorine, also a nonmetal. Both found on the right side of the periodic table. And if you wanted to use sort of a process of elimination, right, you would start looking for these on the right side, see that, oh, they're not there, and then assume if they're not a metal, and they're not a metalloid, then they're a metal. Or sorry, if they're not a nonmetal, did I say that correctly? Nonmetal, metalloid, they must be a metal. Titanium, metal. And then SB is antimony. And that is a metalloid. Yeah, SB is a tricky one. Okay. Moving on then. So we also talk about the periodic table again, right? So we talked about yesterday, right? Classifying matter, classifying energy. Now we're classifying atoms. A lot of this class, if you can get it into your mind and you can group these things in your mind, it's going to make them much, much easier to work with. Instead of trying to, by rote memorization, try and figure this out. That's why we put things into groups. So we have what are called main group elements, right? That's the left side here. And then we have also on the right side over here. These are our main group elements, and their properties are fairly predictable. When you get into the transition elements, the properties it's a little more dicey. You don't know based on where they are. There are some trends. For example, depending on how much you know about electronics and stuff, right? Copper is a really good conductor. If you want to get a good audio cable or maybe even a charging cable, you want copper. But you might also know that silver and gold are also really good conductors. So these properties do sort of trickle down or do follow down the periodic table, even for transition metals, albeit they are less predictable. So when we talk about the family, each column is a family or group of elements. So those are interchangeable, right? We can say this is a family, this is a group. It means the same thing. Some of these groups have names. So we have the alkali metals, the alkaline earth metals, we have the halogens, and the noble gases. And just as a little bit of a bonus, this 6A column, these are called chalcogens. I don't think there are any test questions on that, but little bonus, chalcogens. So the alkali metals, right, this is column 1A. Oh, that was a point I wanted to make as well. So notice that on this periodic table, we have these as 1A and 2A. And then over here, it starts at 3A, 4A, 5A, 6A, 7, 8, right? All with the A. There's another numbering system that can be used that doesn't include the A. So instead of 1A, this would just be 1. Instead of 2A, this would be 2, and then it goes 3, 4, 5, 6. So remember, when we're talking about these main group elements, make sure you're using the 1A, the 3A, the 4A, because there is a difference. But our 1, and that's why here too, right? So we have the 1, 1, and also, do it in a different color, 1A. So our alkali earth metals is our first group, the first column, the first family. All kind of the same thing, but I'll use group from here on out. The alkali metals are very reactive metals. Oh shoot, I meant to look up a demonstration of this. If you take these metals, lithium I think is, or potassium is the most common one. You can take potassium, pure potassium, and throw it in water, and it explodes. And as you go down this column, their reactivity increases. So cesium is even more reactive than rubidium, which is more reactive than potassium, and so on. Those are our alkali metals. We have our alkaline earth metals. So now we're talking about group 2A or group 2. The alkaline earth metals are fairly reactive. Not quite as much. In fact, you can get computer cases that are made out of magnesium. You can also get wheels for your car that are made out of magnesium. Magnesium is also used in fire starters. So if you know anything about camping, if you've done much, you might have a magnesium fire starter. On one side is a block of magnesium. It's not too reactive. When you've got it just holding it in your hand at room temperature, it's fine. But if you shave off some fine pieces and then use the other side of the fire starter to create a spark, if that spark lands on the magnesium, magnesium burns incredibly hot and incredibly bright. There have been some accidents where car tires, people weren't so good at parking, ran their car tire and their wheel into the side of the curb, and that can ignite the magnesium and then ignite the tire, and then you've just got an overall bad situation. But again, reactivity increases as you go down here. So those are our group 2. Now, we're flipping all the way over to the other side of the periodic table to group 7A. This is our second to last named group. These are the halogens. They're also very reactive. You may be familiar with chlorine because it's in sodium chloride, which is table salt. I think reactivity for 7A is actually the inverse of the alkali and alkali earth metals. So fluorine is the most reactive, while acetine is the least reactive. I'll write this reactivity. Yeah, reactivity. Now, our noble gases, right? So now we're on group 8A, or 18, column 18, the very last column. These are the noble gases. They're chemically inert. Helium we know from balloons. Neon we know from neon signs. You might know that argon is actually used in double pane windows. And it's used in double pane windows because it's so non-reactive. If you were to use something else like regular air, you can get some reactions happening and it'll cloud the glass on the inside, which you obviously can't clean. Krypton is not kryptonite, it's not Superman's weakness, but I do believe that's where its name comes from. Right. Oh, I did want to make a note too. Neon signs don't glow because the neon is reacting. Just wanted to make that clear. Okay, so Skillbuilder 4.3. We have another poll. So go ahead and take a look at these elements here and write down which group they're a part of. And so I listed all of these as group using the A, right? So 1A, 2A, 5A. So go ahead and find them in each column. And again, here you can kind of shorten your work, right? Because it's multiple choice. So you can check 1A, 2A, 5A, 7A, 8A for lithium and sort of eliminate your options there instead of checking the entire periodic table. And again, I'll just give you like a minute and a half or so for this. This is especially good practice because it gets you familiar with the periodic table. And the exam tomorrow is going to be timed. So you do have about a minute and a half per question. But, you know, the faster you can knock these questions out, which is really just finding it on the periodic table sometimes, the more time you have for the other calculations or the problems that you might have a more difficult time with. All right, just a few more seconds here. I'll leave the poll up just in case you want to finish it out, just to complete it. So lithium is in 1A, and that is, oops, if I can spell, that's an alkali metal. Boron is in 3A. That group doesn't have a name, but, you know, as a little bonus, I believe it's a metalloid. Iodine is in our second to last column, right? So that's 7A, and that's a halogen. And argon is in 8A, and that is a noble gas. All right. Good job. Everybody got those ones right. Now, when we talk about chemical reactions, atoms are often losing or gaining electrons in those chemical reactions to form these charged particles called ions. Positive ions are called cations. Negative ions are called anions. I thought I had a way to remember this. I can't remember. It might be just the kind of thing, again, this is another flashcard you can make, right? Positive ion, cation. Negative ion, anion. You might remember that the prefix "an" can mean without. Anhydrous would mean without water. So negative ions, meaning it's negative. Weak way to remember it there. The charge of the ion is shown in the upper right corner of the symbol. So we would write something like calcium 2 plus. So we usually write it with the magnitude first and then the charge second. So you could also have something that has a single charge, so you could do chlorine 1 minus. And when it's 1 minus, if you really want to, if it makes you feel better, you can write the 1, but you don't have to, it's implied. Or you might have, just to do another negative example, oxygen 2 minus, right? So we write the number first and then the charge second. In our reactions then, we might have a reaction like this where a lithium atom loses 1 electron, E minus is how we write an electron, shorthand, to form a lithium positive ion. And so the charge of an ion depends on how many electrons were gained or lost. So if we have a neutral, so it's dependent on the number of electrons charged or gained or lost. So if we have lithium, for example, I have a periodic table here. Well, that transition took longer than I thought it would. If we look at lithium, and I can't write on here, but lithium, you there see that top number, right, is the atomic number. The atomic number is the number of protons. Lithium has 3 protons. So, let's go back to notability. Wait for it to show up. So you see lithium. Oh, right. So it's going to be neutral lithium. Neutral lithium has 3 protons. I'm just going to abbreviate it 3p. And neutral lithium is going to have 3 electrons, right? Because our charges then cancel out, and so we end up with lithium with a 0 charge. So then if we have lithium up here losing 1 electron, then we might write that lithium has, right, 3 protons minus 1 electron. Why am I having a hard time with this? Because this is going to equal then... Oh, sorry, lithium... Yeah. Lithium loses an electron, but its positive charge is not going to be +2. For the lithium ion with 3 protons and 2 electrons, 3 minus 2... Oh, I see. The number of remaining electrons. So if you look at it like this, right? So we have lithium. If we have lithium and we remove an electron, now lithium has, we now have lithium with 3 protons minus 2, minus the remaining electrons, right? Because we removed 1 electron, we had 3, we removed 1. So our charge is going to be plus 1. Does that make sense? I know that was... this slide was not very clear. So, to calculate the charge of the ion, yeah, it's the protons minus the remaining electrons. If you have something, a reaction like this one. We'll have some more examples. Okay. So, in this reaction, we have fluorine gaining 1 electron to form F minus. So I happen to know that fluorine, has 9 protons, and we added 1 electron, right? So now we have 10 electrons. So we do 9 protons minus 10 electrons gives us a 1 minus charge. Okay. I don't have a poll for this one, but we're going to do it together. So we have a nickel ion with 26 electrons. So first we need the atomic number for nickel. So I'm going to look it up. Oh, that's not what I wanted to do. So that takes way too long to transition. So I know where nickel is. Okay, so nickel has 28 protons, right? Nickel, the atomic number is 28, which means 28 protons. So we have 28 protons minus 26 electrons. Our charge then is going to be 2 plus. So if we look up bromine, bromine then has a atomic number of, right, Z equals 35. So now we have 35, and that's equal to 35 protons minus 36 electrons. And so now our charge on bromine is going to be 1 minus. And so we would write that as, and I should do this too, right? So for the nickel, Ni, 2 plus. And we would write Br 1 minus, or like I said before, Br minus. So then for phosphorus, our atomic number is going to be, right, so phosphorus is in 5A, and it has 15, an atomic number of 15, which means we have 15 protons, minus, how many electrons do we have here? 18 electrons, to give us a charge of 3 minus. So we get P3 minus. And try to, like, when you do these kind of problems as well, just, you know, we see bromine. If you see it's in column 7A, remember 7A is halogens. Just kind of incorporating everything we learn at every step, even though a question doesn't ask for it, reminding yourself of those things can be helpful. Okay, so let's find the number of protons and electrons in an S2 minus ion. So, what element is sulfur? I gave it away. S. S is sulfur. So sulfur has 16. All right, so you're going to always start with, unless it's given already, start with finding the atomic number, 16, which means we have 16 protons. Now, instead of being given, So we've got our equation here, number of protons minus number of electrons. This is equal to our charge. So a little bit of algebra. We can sort of plug these numbers in and then solve for the number of electrons. So what we'll do is we have a charge of 2 minus. So we'll go 2 minus is equal to 16 protons minus a number of electrons, which is what we're looking for. So when you do this, you might want to then say our charge is we have a -2 charge, so that you remember that this is -2 when you do the algebra here. So then we're going to subtract 16 from both sides to get -18. -18 equals the negative minus the number of electrons, right? So negative, positive. You can't have a negative number of something. But we have 18 electrons then. Cool. Oh, I mentioned this already. The number associated with the letter A above each main group column in the periodic table, 1 through 8. So right, we have 1A, 2A, and there's also 3A through 8A on the right side, gives the number of valence electrons for the elements in that column. You could think of valence electrons as the outermost electrons in an atom. For example, main group elements tend to form ions that have the same number of valence electrons as the nearest noble gas. Right, so we have valence electrons. So these are the elements that form predictable ions. So if you look at, they don't have them here. Oh, let's see, what is this? Because this is helium. This is, neon, argon, krypton, and xenon. So each of these, on this side, these have 8 valence electrons. Kind of ran out of space there. They each have 8 valence electrons. So when we talk about the nearest noble gas, we got to remember that you can go backwards this way too, as well as forwards, right? So lithium and beryllium, they're trying to go back to become helium. Same here. So these are going backwards to become neon, or not to become neon, I shouldn't say that, to become like neon. They all want to have 8 valence electrons. And then things like oxygen or fluorine are going to move to the right, because this is closer than going all the way back around the periodic table. Yeah, and transition metals, they'll form cations with they're wacky, they're weird. And that's why too, when you look at aluminum or gallium or indium, you might think, well, why are those forming a 3+ charge? Because this looks like it's closer. But you got to remember, we're ignoring this. We're just considering 1A, 2A, and 3A. So it's shorter to go from 3A back around past 1A to get back to 8A than it is to go forward this way to 8A and gain electrons. All right. Okay, so let's, based on their position in the periodic table, what ions do potassium and selenium tend to form? Or take a minute and think about it. Think about where potassium and selenium might be. If you can go ahead and try and find them, I'm going to find them on my periodic table. Well, I know where they are, but take a minute and try and find them on your periodic table as practice. So for potassium and selenium, and what their atomic symbols might be. So we have selenium. And actually what I should do maybe, let's see if I can do this. Just copy this photo. Paste it. Oh, that's not too bad. I was afraid it might be huge. Okay. So I got a periodic table. Very nice. It's small, but we'll zoom. Okay. So we have selenium over here. right? So we have selenium. So what charge do you think selenium might form? We're going to the nearest noble gas. So we're going to move from 6A to 8A. And then remember, for each column that we pass, we're going to add 1 electron. For each column that we pass going to the right, we add 1 electron. And for each column going back to the left, we will remove 1 electron. So from selenium, we go past 7A, so that's 1 electron, and then we get to 8A, that's 2 electrons. So selenium is going to gain 2 electrons. Its most likely ion is going to be 2 minus. Now if we go to potassium, over here on the left side, again, you got to remember that we can go backwards around the periodic table, and really what we're doing is we're not just going backwards, but we're going back, and we go up a row. So we go back and up a row, we're moving to the left, move 1 row to the left, then potassium's most likely charge is going to be 1 plus, or just a plus. So within an atom and within an element, we always have the same number of protons. But the number of neutrons, right, that's the other sort of heavy particle in the nucleus. The number of neutrons can vary. So all atoms from the same element do not have the same mass, because we can change that number of neutrons. And this gives rise to isotopes. So isotopes are atoms with the same number of protons. So really, for the vast majority, the same properties, and but just a different number of neutrons. They have a different mass. All elements have their own unique percent natural abundance of isotopes. We'll talk about what that means here. So for neon, there are 3 naturally occurring isotopes. We've got neon 21, neon 22, and neon 20. So what does that number mean, though? And you can see here that they occur in different levels of abundance, right? So 0.27%. So sometimes easier if you write 2 zeros, right? Because 1 or 10% would be like this. 0.27% are going to be your neon 21. And then we get 9.25% is neon 22. And the vast majority, 90%, are neon 20. So when we write these out, that 20, 21, 22, that is the number, the mass number, the atomic mass number, right? So it's the number of it's the number of protons plus the number of neutrons. That's what we have here, the mass number. So we look at our atomic number. If we have the atomic number and the mass number, we can figure out the number of neutrons that isotope has. And we do that here. It's an equation, but if you think about it, you can figure it out as well. So the mass number, we use A for the mass number. And the mass number is the sum of protons and neutrons. So the number of neutrons in an isotope is the difference between the mass number and the atomic number. We'll do an example here. So let's say we have, this is just another way to write the isotope. It's another notation. So you can do neon 20 as like Ne-20, or neon, write it out, -20, or 21, or 22. This form is not as useful as the previous form that we saw. How many? Neon has 10, right? So we could also write neon as Ne for 20, and then 10 protons, or its atomic number. So what are the atomic number, mass number, and symbols for the chlorine isotope with 18 neutrons? So again, we'll have to go to our periodic table, and I guess I can just paste that here again, huh? There we go. Oh, good, they're finally fixing my broken sprinkler. My very own Old Faithful. It goes off at about 12:45 every night. Anyways, so if we find chlorine, right over here. Whoa, I think I moved it. Anyways, chlorine is here. And so we have our atomic number, right? 17 also. Again, right? So make note. We have chlorine. Chlorine is in group 7A. So that makes chlorine a halogen. In group 7A, we could even think about what is its most likely ion. It's going to move one to the right. So chlorine 1 minus is the most likely ion. These are all kind of things that as you look up each of these, if you can check these boxes in your mind, you're practicing way more than you would otherwise. Even though all we were asked for here is the atomic number, mass number, and symbol. So we've already got the symbol, chlorine, Cl. And we know the atomic number, which goes in the bottom left, is 17. And we were given a number of neutrons. So we have an isotope with 18 neutrons. So to figure out the mass number, A, we simply add the number of neutrons and the number of protons. So we have 17 protons, and 18 neutrons. And this is not an official notation to use P or N. I'm just using it here, one, to emphasize that you should write down your units. But two, so we can keep track of things, and when you come back later, you know what we're writing into each place. So then that'll give us, I should have wrote this the other way, but A equals 35. And so then the isotope symbol for chlorine with 18 neutrons is going to be 35 on top and 17 on the bottom, or you could also write Cl-35.
When you said the mass number will equal the atomic number plus the neutrons?
The atomic number plus the neutrons, yes. And so vice versa, right? Like if we were just given, this symbol, I'll do this in red. If we were just given this and asked how many neutrons we had, then we would essentially rearrange, we would rearrange this equation to say that our mass number, which is A, 35 equals our number of protons, right? We know our number of protons from the isotope symbol, 17, plus how many neutrons. And so we can subtract 17 from 35, and we'll get 18 neutrons. Here's another example, right? So we have potassium. Oh, I forgot to go over that question. I'll cover it at the end. We'll go over that. Somebody had a homework question. And so, again, what do these numbers mean, right? 39, 19. I'm asking, you don't have to answer necessarily, but think about it. So on the bottom here, again, we have our atomic number, Z. Don't forget, atomic number Z. As confusing as it is that the mass number is A, it just is what it is. So we have our atomic number and our atomic number here, and our mass number here. And so we can then write out this equation that we have, or if you think about it, right, our mass number is the sum of the atomic number and the number of neutrons. But we'll write out the equation. A equals Z plus neutrons. So then we can say, we can just fill in these numbers. 39 equals 19 plus neutrons. 39 minus 19 is 20. And that's equal to our number of neutrons. And just for the sake of completeness here, Z equals 19 protons. Cool. So when we talk about the atomic mass, because we have, and you may have asked this question to yourself as well, why on the periodic table are the atomic masses not whole numbers? And this is because we have isotopes, and the atomic mass on the periodic table is representative of those isotopes. And so each of those then contributes a proportion to what that calculated number is. And we do that with this formula here. So the atomic mass of each element listed in the periodic table represents the average mass of the atoms that compose that element in nature. So the naturally occurring proportions. For example, for chlorine, 75% of chlorine is chlorine 35, but there's also 24% of chlorine, which is chlorine 37. And to calculate the atomic mass that you see on the periodic table, you just multiply the percent abundance times the atomic mass of that isotope. Right, and remember they're not exactly one atomic mass unit, so you get slightly not whole numbers. And then for this one, again, it's the abundance, right? This is our abundance, 24% times our atomic mass of that isotope. I believe we have at least one example. So for the general then equation, it's the fraction of the isotope times the mass of the isotope 1, fraction of isotope 2, mass of isotope 3, or 2, fraction of isotope 3, mass of isotope 3. And this will go on, right? That's why there's this dot, dot, dot. This will go on for as many isotopes naturally occur. And yeah, it's a it's a good thing to note. The fraction of each isotope is the percent natural abundance converted to their decimal values, right? So on this previous one, we are converting 75.77, just divide by 100 to convert it to its decimal value of 0.7577. Magnesium has 3 naturally occurring isotopes with masses of 23.99, 24.99, and 25.98. The natural abundances are as given. Calculate the atomic mass of magnesium. So again, you can just look back at the previous chart, right? We're going to take the fraction of the isotope as its decimal value, multiply it by the mass of the isotope, and then add all of those together. So we'll take, we'll write over here, right? We're looking for atomic mass. I'm going to write average to distinguish that, right? It's the average atomic mass. And we just have 3 isotopes here. So first we're going to do, and these are respectively listed, right? So to follow the exact formula, 0.7899 times 23.99, switch to a different color, plus 0.1000, conserving our number of significant figures, times 24.99, plus, I'll find a third color here, 0.1110 times 25.98. And this is one of those, I think this is one of those problems. If you use parentheses on your calculator, it'll definitely get it right. But just make sure that your order of operations is going in correctly. So I'm doing it in my calculator right now. I'm using parentheses to be cautious. If one of you could also be doing it, and then we can compare at the end and see if one of us has made a mistake. Forgot parentheses. I could also look up, I don't know if this is something that you guys have a hard time with, using calculators and typing in the number. So but I can look up, I can get an on-screen calculator so you can see exactly what I'm doing Maybe I'll do a poll or something. Oh, average. Average atomic mass is then 24.33, right? And then again, well, you could write AMU would be the units. Since we have 4 significant figures at every part, and we have more than 4 decimal places for every step, we maintain our 4 significant figures. Cool. Any questions? Nice. Thank you, Mel. Same answer. Because that is it for chapter 4. The very short chapter. I can hang out here if you guys want to stay and ask questions, or I will, for the next couple hours, I'll be on Discord in one of the study rooms if you want to pop in there and ask questions there. Oh, I almost forgot. I had that question about... Should pop up for you guys real quick. Okay. So you probably can do this now. I'm going to do 74 because you already have the answers for 73. I did post 2. I posted in the Discord, so if you're not in the Discord, you wouldn't have seen it probably. Is there a way I can make notes here? Apparently I can't make notes on this, so we're going to have to do a screenshot. Copy. Here. And there's a blank piece of paper here. And we can make this bigger. Sorry if the screen moving around rapidly makes you motion sick. Anyways, okay, so I did post my Dr. Kurt Kawagoa, who, yes, is my dad. He also teaches at Reedley College. But he has the all of the question sets and the answers from the back of the book for the 4th edition of TRO. So on the homeworks for each module, I do have the problems for the 3rd edition, I believe, all the way up to the 6th. So you can go back, and if you want to use those, you can use those. And if you don't have the book yet, you can find those answers there, or the questions there, and then the answers from the back of the book. You might have to do a little bit of matching to make sure that you're doing the right problem if you did the 6th edition question set. But you now have that available to you. Anyways, so the question was for problem 74, 73, and 74. And now that we've gone through the chapter, we did some of these problems early on. I wanted to do them then. But for example, A, if we have magnesium, and that magnesium loses 2 electrons, knowing that we're starting with the magnesium as a neutral element, we can then just say that it's magnesium 2+, right? Because we have removed 2 electrons from magnesium, and then we've changed the number of electrons by 2. So it's 2+. For barium, in this next one, we have barium going from barium to barium 2+. And how do we remove, or how do we change the charge? We remove electrons. So we've removed 2 electrons, and that would give us the proper charge on barium. They flip it around here for question C, and they're adding 1 electron to iodine, which, if you look at your periodic table, you'll know that iodine is in column or group 7A, which makes it a halogen. And from today we learned that halogens are most likely to form -1 ions, or 1- ions. So in line with all of that other information, as well as being given that we've added an electron here, you'll know that iodine makes a 1- charge. And then for aluminum, so you can see here, so we got aluminum again, and then on the right side it says +3 electrons, which means we've removed 3 electrons from aluminum. So we'll get Al 3+, just like that. And then it's exactly the same thing for 73. So now you can practice those, check them in the back of the book. Are there any other questions? Alrighty. I have also decided, I should have put this in the announcements as well. I don't think the lab watch parties is necessarily the best use of our time. Instead, I will make that an office hour. So I'll have an office hour now from 2 to 3. At least 2 to 3. We can go longer if people are around. And then I'll do another office hour in the evening from, let's say, 7 to 8. I'll be on Discord. I'm usually right here in the evenings anyway. So I'll be here. You can look for me in the evenings or in the afternoon. I believe Discord shows if I'm on or not. But if you send me a ping, even if I'm not at my computer, I'll get it on my phone. And we can set something up and go over some problems. Alrighty, that is it for today then. We've got this homework to do tonight. The lab from yesterday is actually not due till Friday, which was a typo on my part, but to your benefit, I suppose. Yeah, so study for the test. Good luck. Remember, you can always contact me if you have questions. All right, I will see you guys. Oh, actually, I won't see you tomorrow because tomorrow there's no lecture. It's just the test. So I'll see you on Friday at 10 a.m.
Can I ask a question right now?
Absolutely.
It's about the unit analysis worksheet.
Sure.
I was doing the first one, and I'm assuming the first two fill in the blanks are what that letter represents and then the number that it represents.
Yes. Let
Is
me
that
pull up
true?
let me pull up the unit analysis worksheet so I'm looking at the same thing. We also have a tutor, an embedded tutor now. So I'm working with her to get her on board. Canvas is cool and all, but it's kind of clunky. You know, it clicks so many things. Okay. I now have the unit analysis worksheet. Oh, yeah, I believe there's a video on here as well, right? Yeah, to do the first couple problems. Yeah, so you're supposed to put, I think the label, right? So for capital M would be mega, and that's times 10 to the 6.
Okay, yeah.
Yeah, and
Just
then
wanted to double check.
for megagrams, right? That's I think the way you do that would be 1 megagram is equal to 1 times 10 to the 6 grams. Yeah.
Right. I just didn't have access to the video right now, so.
Okay. Yeah, let me double check here. So this video for how to do it. Yeah, they put it's actually a video. It's funny. Both of my parents teach one of them teaches at Reedley College, the other teaches at Fresno City College. So this video was actually my mom. So yeah, if you put 10 to the 6 in the first box and then mega in the second slot, and then for 1 megagram would be 1 times 10 to the 6 grams. If you've already done some of them and you flipped them, don't worry about that. I'll figure it out.
Okay. Thank you.
Okay. Any other questions before I sign off?
Yeah, so tomorrow it's just going to be the exam.
It's just the exam. So in reality, you have all day to study if you want to take it in the afternoon.
Yeah, that's probably what I'll do. So that's good.
I will try to be available too, kind of all day. Yeah, we'll see how this goes.
Thank you.
All right. Anything else? Oh, yes, I can upload the key for that. Sorry, I forgot I said I would do that. I'll do that right now. And I'll upload it on that same page. All right. Thanks, guys. We'll see you on Friday.
The recording has stopped.